Does anybody know what SLOPE stands for? That was the first question. Very good. It's funny, as soon as we have little kids in here, they'll say rise over run or something like that. So most people understand or know it because we have a slope in here. We've actually been kind of branching out and not just doing lunar work, we've been doing some Mars work as well. But the main purpose of this lab is to simulate the terrain conditions on the moon or Mars so we can build better tires, better technology, do IFU research, mobility research, all these things that will help us explore greater regions and do what we want to do out in space. So next question for you guys, before I tell you what some of these simulants are, I want to take a poll. We got two different beds of soil here. Now without touching them, without knowing anything about them, which of these do you think would be harder to drive in? Say you had an ATV or something. So we'll say who takes the stuff on the left is harder to drive? Who takes the stuff on the right? And who has no idea whatsoever? What's this? So we're going to do an experiment to find out. I need one volunteer. You guys are all welcome to do this too. This is a fun one. So I want you to take this tire rod and to see how far you can plunge it into this material. That was good. All right.
That was awesome. A lot of marbles.
That's awesome. It's about 8 inches or so.
Okay.
I'll go to this one. We'll try it again. That's awesome. You're the perfect subject.
Over dramatic, yes.
Yeah. You also want to try it? No, I'll just leave it right here. So the reason I kind of asked it that way is because that's how the operators of these Mars rovers that are currently driving around on Mars, you guys are probably aware of a lot of them, pictures up there. I'll just talk about kind of Curiosity right now, the most recent rover that's been driving on Mars. All the decisions for the most part that are made in terms of how they're going to drive, where they're going to go, whether they should stop, turn around, back up, things like that, are based on images that they get here on Earth. And those images are usually not taken in real time. Actually, they never are taken in real time. There's a huge communication lag between Mars and Earth, sometimes up to 30 or 40 minutes. So when the operators are controlling these rovers, it's not like they're sitting in a lab with a joystick and a screen just driving around with a remote control car. They're getting all these images and data, and then they're making a decision: should we go forward? Should we stop? Should we go around? A couple times rovers have actually gotten stuck on Mars with material very similar to this. We call this our Mars sink tank. Now the material that the rovers actually got stuck in, unfortunately we don't know a whole lot about its chemical composition and material properties because we never sent humans to Mars and never brought any soil back. Yeah, we're hoping to do that soon. But based on how the vehicle performed, we're able to kind of recreate that condition here on Earth. So that's the stuff on the left that you're so easily able to plunge that stick into. It's actually material called phyllite. It's used as a filler in concrete, but it's hollow microspheres. They're round, they're uniform in size, so that they don't stick together, they don't compact. If you were to drive a rover on this, you would probably get stuck and not go very far. If you were to walk in this, you would actually sink up to your knees pretty quickly too. So this, in our mind, this is kind of like the worst case possible. We don't want to drive in it, but if we do, we're going to make sure we don't get stuck. Because this stuff is actually pretty common on Mars. Twice rovers have gotten stuck in it. First time, are you guys familiar with Opportunity? Of course, that rover just was retired a few weeks ago. But a year into its mission, it actually got stuck in soil like this. And to get it out, they literally just spun the wheels nonstop for a couple of weeks, maybe moving a half an inch or so a day at a time. But it got out of that. And a couple of years later, Spirit, the sister rover to that, for those not familiar, Spirit and Opportunity are identical rovers. They're the ones second from the right. Spirit got permanently stuck in a situation like this where they just could not get the rover out. So that communication lag, coupled with the unknown nature of the terrain and the difficult nature of the terrain, has made driving rovers on Mars very, very, very challenging. So the stuff on the right, again, I'm not going to talk too much about it. This is a material called GRC1 that we developed here in-house to simulate the lunar terrain. This is actually based on data that was collected during the Apollo missions to the moon back in the 60s and 70s. Not so much on soil that was brought back from the surface of the moon, but on data that was actually taken from the astronauts and from the vehicles themselves driving around. So, in other words, driving a rover on this is comparable to driving a rover on the surface of the moon. Now, we do most of our vehicle tests in this material. We have a test rig over there. We can test out individual wheels and excavation tools over various simulants. At the back, we have an adjustable tilt bed. Another fun pop quiz question. What angle would you guess it's at right now? 90 would be straight up, 0 would be
45.
45.
30.
30. 20. So that's actually, you guys are pretty close. I don't know exactly, our inclinometer is missing, but it's 25 degrees.
25.
A Most people will guess higher, and actually you guys are pretty close. Most people come in and say 50 or 60 degrees. It's very difficult to look head on and make that estimation. If you look from the side, it's not so difficult. Are you guys skiers? Yeah. So if you go down a black dining wheel, double black dining, what's the slope on the 30 degrees? Yeah, but it probably feels like a cliff.
Yeah.
Okay. Yeah. So 30 degrees, 25 degrees is very, very, very challenging to get up. The steepest slopes that the rovers are required to climb on Mars and the Moon right now is 15 degrees, which sounds pretty pathetic until you see it in person. That's actually pretty difficult to climb up. Now the tilt bed can go up to 45 degrees. However, the soil has what we call a natural angle of repose of only about 37 degrees. So this is the geothermal material. As you start to go up, you see it reaches about 35, 40 degrees and starts to spill out. So if we were to actually raise that tilt bed up to 45 degrees, most of the soil would start spilling out. We'd have a huge mess. So.
When we talk about rovers for Mars specifically, these are the three classes of rovers that we've dealt with over the years. That little itty bitty guy down there in the bottom lower left is the, if you guys ever watched the movie The Martian with Matt Damon, it was the rover he was talking about that he went to go get parts from and it was buried or whatever. He actually got the name of the rover wrong. He called it Pathfinder in the movie. That was the name of the mission. The actual rover's name was Sojourner. So if you notice that was the first rover that we sent to Mars, and you can see the size of it is very, very small. So a very, very, very small rover, okay? So we didn't need to carry a lot of mass, and so because of that, those wheels were solid aerospace grade aluminum. Okay, when we went to the next class of vehicle, which is, there in the left quadrant, more left upper, that is one of the two sister rovers Colin talked about, which is Spirit and Opportunity. Opportunity wasn't the one we just retired. Those particular rovers were about 400 pounds. And so what they basically did was they scaled the tire to try to meet the load requirements. Okay, because the history was a solid, rigid aluminum wheel. The current rover that's on Mars right now is the one over on the right. That's about 1 ton, so a 2,200 pound rover. And those MSO wheels that are on that's Curiosity. And we have a flight spare over here that you're going to see, and you guys can all hold it. Those particular wheels were again scaled because of legacy in order to try to do this particular mission. And the issue with that was in order to meet mass requirements, the skins on those, which you'll see, those are actually thicker skins. The skins on the actual flight wheels were 0.7 millimeters thick. Okay?
So won't pass this around, but we'll put it back up there to watch it. Solid aluminum. Everyone thinks it's plastic. Like Santa was saying, the thickness of these is 0.7 millimeters.
And the issue there was, if you guys have seen any of the stuff of pictures from Mars, the regolith that is actually on the trajectory that they've been traversing is extremely tortuous compared to what we were expecting. And that's creating high localization in terms of the forces on any given element, material element in the wheel, and it's causing a fracture and puncture of the skin. Okay, so much so that they've actually had to slow the rover and actually stop at almost every obstacle and take imagery to decide whether or not they can go over it or they need to go around it. Yes, it is.
Yeah. So, one thing I'll mention before we talk about that, they even recently, some of these grousers, chest pieces have snapped too, and that was originally kind of designed to be the backbone of the tire, but these would hold the load, the skin in between would prevent them from sinking too much, but it's just, as we found, it's just a very unforgiving terrain. It's a big, heavy rover.
Are there sensors within that each wheel that can also detect punctures, or is it
No.
more you guys looking at it? It's
Purely visual odometry and other types of inspection. Optical.
So it sounds like at least some of you are aware of this interesting story. So all the Mars rover work is led out of JPL, so Jet Propulsion Laboratory. And when they first designed this tire, they wanted to use visual odometry to track movements and estimate speed and how far they travel, which is something they've done for a long time. So the idea is you put a unique tread pattern in the wheel that would show up once per evolution, after you drive so far, you turn around, turn your camera on, take a picture of the tracks, and based on how far apart that feature is, you can estimate how fast the rover is moving, how far you've gone. So JPL engineers, being like any engineers, they said, let's spell out JPL in big block letters all over Mars. That'd be cool. But there are, 10 NASA centers? So the other 9 probably weren't as crazy about that. So they came back and put these rectangles in. But in Morse code, this actually spells out JPL. Here it is.
So, knowing that we had this issue about 7 years ago, 6 years ago, somewhere around
Head
there.
over to the table. So
Yeah, let's come over here. The group that was working on tire technology, we call mobility elements, started to look at what can we do to basically make a mobility technology that overcomes the limitations that you have both in terms of durability and in terms of traction performance, in order to be able to develop a technology that doesn't suffer from what these kinds of technologies are suffering from. So what they did is they went back to the old Apollo days where we had a technology that was compliant, as you can see. It's a compliant tire technology that the Apollo engineers designed for the rovers for the moon back in the 60s, 70s, in the 70s really. So what you have in this case is basically a mesh that is comprised of spring steel, okay? And the engineers back in the day were really good because they understood mechanics. And when we have a deformation field in mechanics, that field is actually comprised of 3 different deformations, okay? One of those deformations we can show on a full structure or element is if we took this structure and we just moved every point in space, it's what we call a translation, okay? When we do this translation, there's no strain to the material element, okay? So this material could do this all day long and it doesn't have any damage. There's another deformation in mechanics where if we took this structure and we moved all the material elements like this in space, it's what we call a rotation. And again, we didn't do any strain to the material element, so that would last forever, okay? There's a third deformation, which is what the problem is in here, that happens in mechanics, and it's called strain. It's when we actually have that material element point actually elongate and stretch as a material, and that's the one that can create damage and issue inside of a structure, okay? If you exceed the limit in strain that the material itself can do, that's when you run into problems, okay? So if you'll notice in this structure, we can do large deformations of translation and rotation. I'm going to show you right now. Did you see that large deformation? Just translation and rotation without getting any strain. And that's what allows this structure to work up to a point. If you notice inside of the structure, and we're going to, only 2 or 3 minutes? Great. So if you notice inside of here, there's another structure in there. We call it a bump stop. That limits the deformation that we can do in this structure, so that the material doesn't exceed that strain limit before it starts to have problems. And unfortunately, since we have a limit in time, we're going to go to another part. So if we were to take a piece of spring steel in a different type of structure, we call it spring, and we were to deform it a little bit, you can see that it returns to shape and we don't have any problems. Okay? But if we go a little bit too far in that deformation, you can see we kinked it. And that's what we call plasticity. This is a product of the way conventional materials deform and behave. In this case, we only have 0.3% of that element we called strain, where we're elastically stretching the bonds between the atoms. We go beyond that, we start breaking them, and we get irreversible deformation, and eventually fracture, which is what's happening in here. This has gone even farther beyond that point, and it's just fracturing and failing. But what I do, I came into this, so I'm a material scientist, and our group has been developing, really extending the development of a new alloy system based on nickel and titanium And these materials, we call them shape memory alloys. And in these materials, we, instead of using that elastic bond stretch as the mode of accommodating deformation, we are actually rearranging the atomic structure in the solid state to accommodate the system. That rearrangement in the solid state, which we can reverse back and forth, can do 30 times the deformation potential that we could do in a conventional structural metal. Okay, that lets me take a structure like this, and it lets me fold it back on itself and try to kink it. No issue of deformation. Okay, so 30 times the deformation we can do. So what we're actually doing is that
I thought it was in front of you, so that's not on me.
what we're doing with that for the Mars program is we're developing what we call spring tires made out of those unique classes of materials. Okay, so what we end up doing is we take two springs and we weave them together just like a chainmail, and we make an entire sheet of those springs, and then we fold the ends of those back on each other and finish it with another spring to form a cylinder. Okay, once we form that cylinder, you can see there's like two beads on here. Somebody want to help me? Who wants to help? You want to help?
Yeah.
I'll tell you, we're going to just push our hands together.
Okay.
When we take those two bead ends and we push our hands together, we pop it out into a toroid, which is the tire. Okay? So that's how a tire like this is actually constructed. And when we make it in terms of this particular material that we're developing and continuing extending here at Glen, we can take that entire construct of tire and not only carry much higher loads, we can deform that structure all the way to the axle and it would return to shape. Okay? So infinitely beyond what any of these other prototype type concepts could do.
That's the one that's being passed around. Well, this is one of the versions.
Is this axle 3D printed?
It is.
Yes,
This
it is.
just a prototype.
Just a prototype.
So it's not.
Eventually it would be in metal.
So if that's the tire that's on Curiosity right now, is it just getting ripped up?
This is the one that's on Curiosity. It's being torn to shreds.
So eventually will it stop moving then because it won't?
Something will fail eventually. Hopefully we'll get the tires first, but that is possible.
The current technology that we're working on in SMA is being looked at right now as one of the potential future baselines for all rover missions. Translations and rotations that we normally would deal with to try to limit the strain, we can go to different types of concepts that we would never try in a conventional material. So as an example, this was constructed, this is one of our other under patent technologies, which is using a radial element, radially stiffened element of SMA, because we know that the arch carries more load than anything else. It's why we build buildings around arches when we talk about compression and flexure. Okay? So we would never try this with a steel or a conventional aluminum or any of our conventional structural metals, because as soon as we would start to deform it, it would plasticize, just like your Slinky did when you took it too far. But this tire, which we built on a regular rim, and we actually tested almost 2 years ago now, out in our west area. I'm coming to you as soon as I say it's done. We carried over 2,000 pounds on this tire on an actual Jeep. This tire could have actually been crushed all the way to the rim and would still return to shape. So those are the things that we're trying to do to extend design ideology. And I guess with that, I gotta.
So you can either go use it for your people, or you can split it up and use it as propellant for your return vehicle. So if you can access that water, you can use it. Mars is even more exciting because not only is there water in the soil and these minerals, like hydrated minerals, like Epsom salts, that kind of thing, there's also subsurface water. If you go to latitudes, even like 40 plus, you can start to find some subsurface water. There's glaciers underneath there too when you get into the higher latitudes. So you have a huge source of water that you can access. And the atmosphere of Mars is CO2. So if you take the C's from there and the H's from the soil and you start to mix all this together, you can actually make methane and oxygen, which is an even better rocket propellant, just with what's available on Mars. So what do we do here? So ISRU is this whole system where we start by scooping up soil, which of course if there's water in the soil, you gotta dig for it, right? So these kind of mobility platforms, all these tires that you're seeing, we're using that to try to figure out how to excavate the soil in large quantities, to gather it up and then put it in these reactor systems, bake off that water, react the soil, and then send that up to clean it up, electrolyze it if we need to into the rocket propellants and use it. So ISRU is a full system issue here that we study here at Mass Glen. And at Kennedy, Johnson, JPL, we have partners all over the place because like I said, there's a lot of different systems involved in ISRU. So we actually use the lab here to test the excavation systems. I think we're going to pop over to the Excavation Lab so you'll see some of the excavation tools that we're actively working on for ISRU right now. I actually work in the back corner, kind of, you can see the cement mixer back there. So I do some tests where I mix water in soils, and I take it over to a vacuum chamber. I freeze them down to cryogenic temperatures, and we test different drilling equipment over in a thermal vacuum chamber. Actually in the facility you're going to see next, but I don't think you'll see our chamber. It's called VF13, it shows in the corner, so if you see it, that's what it is. So anyway, we use that to test the different drilling equipment and whatnot that we use on these surfaces. So it's a really exciting idea to live off the land. Obviously the pioneers didn't take everything with them, they used what was there. So we use both the slope lab and our different facilities to do that. The simulants we use, obviously the big problem is we only have so much lunar soil returned. So we can't use them for quantities of scale like this. And we're talking about making something like 40 metric tons of propellant when we're talking about Mars, and we're talking about something like 10 metric tons of oxygen if we're talking about the moon. So these aren't small quantities that we're talking about to support humans. So you have to talk about big scale excavators and testing with large scale soil. So we have different simulants that simulate things like the different chemical composition of the soil, as well as the different properties. So while these things are great for mobility simulants, they're not necessarily good for reacting with ISRU purposes.